So in the previous lectures we saw how computable measures such as Shannon entropy and even lossless compression have some limitations. Here we will introduce new concepts and alternative methods to measure algorithmic complexity by completely different means as those taken by classical information, and also different or complementary to the use of lossless compression algorithms to approximate algorithmic complexity. We will also see how measuring algorithmic complexity can help in analyzing real-world data and produce candidate mechanistic models, and therefore how it contributes to the discussion of causation. So by now you must remember the most basic definition of algorithmic complexity, or Kolmogorov-Chaitin complexity. The algorithmic complexity of a string, or an object S, is the length of the shortest computer program P that, running on a Turing machine U, produces S. Another suggestive way to read this formula is as follows. The string or object S can be an observation of the world. Then we aim at finding models such as the computer program P that are the generating mechanisms, because they are computer programs that can mechanistically be followed step by step when running on a Turing machine. This interpretation is the same as the one suggested by another area called computational mechanics, introduced by James Crutchfield and others. As we know, algorithmic complexity is uncomputable because there is no algorithm to find and prove that program P is actually the shortest. So what other people have done before is to reduce the power of the Turing machine on which the programs run, and thus of the computer programs themselves. For example, if instead of a Turing machine U is replaced by a finite automaton, a machine that is much simpler, then the quest to find the shortest finite automaton producing a string is actually possible. But this comes at a cost. The simpler the machine or the computational model, the easier it is to find those programs, but also those programs will capture less features of the observation, to the point in which, just like Shannon entropy and other computable measures, they would miss most algorithmic features and would be restricted models mostly to statistical properties. They are of course still very interesting because they offer also mechanistic models. There is an automaton diagram from which more data can be produced to test and model an observation. One can also see immediately from the definition of algorithmic complexity how algorithmic complexity also captures Occam's razor. That is the assumption that the simplest generating model is also the most likely. In this case, algorithmic complexity formalizes Occam's razor by assuming that simple means shortest. This is usually considered a reasonable assumption in science, and it can even be said it drives science itself as we try to find simpler explanations to complex phenomena. From the definition, one can also see how algorithmic complexity offers a way to produce a mechanistic model that is constructible by algorithmic means, as both P, the computer program, and U, the Turing machine, are realizable, meaning that one can actually run it on a digital computer and follow it step by step. One can also see how the model has to be compatible with the observation because of the equality between model and observation, and how this is possibly a very strict requirement, as we would easily accept models that conform with the data and not necessarily a model that produces exactly every aspect of the data, as it would be required from the pure form of algorithmic complexity. In some way, this wouldn't even be desirable because sometimes observations come with noise, and we don't want noise to be represented in the model. And while K is uncomputable, there are means to approximate it because, as we have seen before, it is lower semi-computable, which means, as you already know by now, that one can find upper bounds and make continuous improvements towards values of K. So if we are not proposing popular lossless compression algorithms, how do we propose to calculate K by other means? The answer is by exploiting algorithmic probability and the fundamental coding theorem. The method is based on the idea that, contrary to the big data dictum, that small data actually matters, especially in causation. The main idea is that one can run all computer programs up to some size to see how many of them generate the same string or object, and then we continue running more programs to produce more data that translates into more strings and their associated frequencies, providing estimations of their algorithmic probability. Then, by the algorithmic coding theorem, we can convert those frequencies into an estimation of the algorithmic complexity of the string. The programs will be generative mechanisms or candidate models explaining the data, and the complexity values will serve as a guide for us to compare models across data. As a reminder, the algorithmic coding theorem establishes the connection between the complexity of an object and its algorithmic probability of being produced by a random computer program. The intuition behind the coding theorem is the beautiful relationship between program size complexity and frequency of production. What it means is that the less random an object, the more likely it is to be produced by a short computer program. There is a greater probability of producing the program that produces the object, especially if the program producing the object is short. Therefore, if an object is compressible, then the chances of producing the compressed program that produces the said object are greater than they would be for a random object. By way of the algorithmic coding theorem, one can approximate the algorithmic complexity of an object. So what we do is to look at the empirical output distribution of trillions of small computer programs and count how many times an object is produced. Those objects produced many times will have high algorithmic probability and therefore low algorithmic complexity, and vice versa. Here are two key formulas to understand the method. Let the tuple n and 2 be the set of all Turing machines with n states and 2 symbols. That is, binary Turing machines with n states. And let d be the function that assigns to every finite binary string s the number of machines that produced s divided by the total number of machines of that size. Then d of s is an approximation of the algorithmic probability of s, and by the coding theorem we can obtain k of s. In this case is CTM of s, coming from the coding theorem method. Dn can also be seen as averaging k over a very large set of possible computer languages or computer programs, each represented by a small Turing machine, in order to reduce the possible impact of the constant from the invariance theorem that we covered 2 units ago. Another way to see the method is as averaging over a very large number of short computer programs whose frequency is an indication of their complexity, according to the coding theorem. The coding theorem method allows us to not only build an empirical distribution of computer program outputs from smaller to larger computer program sizes, but once a string S is generated for the first time among all computer programs of the smallest size, we know which Turing machine is the smallest one producing a string for the first time, and also the runtime of such a Turing machine. Here you can see a flow diagram of the algorithm behind our main method. The idea is to start from the smallest possible program and follow an enumeration going through all possible computer programs of increasing length. Length here is quantified by number of states in a Turing machine implementing such computer programs. Then we iterate through that enumeration because we know computer programs are enumerable, just as Turing machines. And we look for the output of each computer program to increase a counter indicating how many times every output has been produced, effectively producing an empirical distribution related to the universal distribution that we will then use to estimate the algorithmic probability of a string, or an object. So we start with computer program 0, which means it has a label 0, where 0 has nothing special but is a small program among all possible that can be carried out by Turing machines with up to certain number of states, starting from 2 states, because one state doesn't compute anything. Then we exhaust all programs of that size, making irrelevant with which we started at beginning, before moving to computer programs that Turing machines with 3 states can run, and so on. Notice that we only explore Turing machines with empty input, and you may wonder why and how could this be a complete exploration of all possible computer programs if we are disregarding possible inputs. This is because Turing universality tells us that one can hard-code programs into hardware and the other way around. This is related to the concept of a stored computer program. You can always copy a computer program into a computer, and it becomes part of the computer. And then you can call that computer program just by calling its name, in this case its number. It is something equivalent to, for example, what we do with our computers, clicking on an icon on your computer. So you no longer introduce a floppy disk or a CD, you just already have it in your computer. So when we go through all possible programs, even with no input, we know we are already exploring the whole space of computer programs, including all those that can be fed or even reprogrammed with non-empty inputs. Once we run each computer program, we then ask if such machine has halted or not, for which we cannot know in general because of the halting problem, but for some cases we can, by, for example, using the values of the BC Beaver, because we know that BC Beaver Turing machines are the Turing machines that run the longest for a fixed number of states. So for that number of states, if a computer program has not halted by the running time of the BC Beaver, then we know it will never halt, and we can then just ignore that computer program because it will never produce any output. However, if it does halt, then we can look at its output and count how many times the same output has been produced before. Now you can see that some outputs will be produced with high frequency, because according to algorithmic complexity and the coding theorem, if a string is very simple, such as a sequence of zeros, then it will be produced by many short computer programs. And in a second, we will see if this is actually the case, because before this very simple experiment, nobody knew. With these results, we can then use the coding theorem and make continuous improvements on estimations of both algorithmic probability and algorithmic complexity, just by exploring larger computer programs. Notice how powerful this is under the charged Turing thesis, establishing that everything that is computable by a Turing machine. It means that we will eventually cover every possible discrete model of natural phenomena if we had enough computational resources. We will see how we can partially circumvent or make a compromise between the lack of enough resources and the power of this scheme. Additionally, from this calculation, we also know which was the first and thus the shortest computer program producing a string, and we also take the runtime of such a Turing machine, which allows us to have an estimation of another seminal measure of complexity, that of Bennett's logical depth, approximated by this same coding theorem method. As you may remember, logical depth is a measure of sophistication that is able to tell apart sophistication or deepness from simplicity and randomness, defined as the computation time that it takes to decompress an object from its shortest description. With this method, we can generate all small computer programs and average their running times to get a value based on this logical depth measure, which we will briefly use in the next unit as an example of an application to a real-world problem related to cognition. The calculation of these empirical distributions related to the universal distribution was everything but trivial, and in some way it hasn't finished and never will. we are still exploring larger rule spaces of longer computer programs to produce a greater number of computable models of the world for our own purposes in our quest to tackle the challenge of causation. The calculation did not only require all sorts of hacks when dealing with running trillions of small computer programs and producing huge numbers of strings and values, but we also had to do with the calculation in the most clever way to save time. For example, we did not run all computer programs because we were able to know which computer programs would produce the same output or a string that would be reversed with some other, just by looking at the behavior of the transition rule of the Turing machine. For example, for each program moving the head to one side of the tape, we know there are the same number of programs going to the other side of the tape, so we could complete the distribution taking into consideration these symmetries. To explore all the computer programs of up to 4 states, it took us about a week on a laptop to go through more than 1 trillion small computer programs. But to explore all possible computer programs implemented by Turing machines of up to 5 states, it already took us a medium-sized computer with 30 CPUs running for 3 months. Currently, we are conducting another run on one of the most powerful computers in the world with thousands of CPUs and GPUs. And we keep increasing the accuracy of our empirical distribution. That is the numerical approximation of a universal distribution. You can see in this table that we also explored other spaces, such as computer programs that print in 2 dimensions and Turing machines with more than 2 symbols to be able to quantify non-binary objects. As an example of one validation and sanity check among many that we performed, we were able to find that we were not only performing in line with what other methods do, such as comparing our distribution with the actual shortest computer programs found following the formalism shown in the previous flow diagram. Because as I said before, from the CTM method, not only the frequency of production of a string is obtained, that is the number of computer programs that produce a string, but we also knew the first time that a string was produced by a computer program, and thus we know which is the shortest computer program producing that string for that computing model. So this figure plots actual instruction size, that is the number of instructions actually used in the shortest computer program found, versus the estimated algorithmic probability for each of these strings, obtained also from the CTM. So for strings from 2 to 12 bits, we found that the correlation was very high, indicating that we were in the right direction. One advantage of this numerical approach to an empirical approximation of the universal distribution is that we do not rely only on having found a short computer program generating an object, but also in averaging all short computer programs found. So the method is more robust than simply finding a single short computer program. This also allows us to generate a set of mechanistic models explaining data. Then we of course compared our results against lossless compression, in particular the popular LZW method using the compress function. And we also found a strong correlation, but we also found that compression was not only limited by the way in which popular lossless compression algorithms work and are implemented, but are also extremely insensitive, especially to small objects, such as short strings, like in this case, only producing a very coarse-grained view with a few distinct values for all the 2 to the n strings in comparison to the much finer-grained values of our methods based on algorithmic probability. Yet what we found is that what was not complex for compression algorithms, that is, what was highly compressible, had also high algorithmic probability, consistent with the theoretical expectation, because remember that high algorithmic probability means low algorithmic complexity, which is exactly what high compressibility means. However, the converse was not as strong, and there we had to look further to find out that the main difference is that our methods were identifying some strings that should be compressed further, but the compression scheme failed to do so. unlike our methods that were suggesting that some of these strings should be of lower algorithmic complexity than what the compression algorithm was suggesting. We will see in the next lecture how we tested this and how that would help us to better deal with causation. So how the empirical distribution looks like? It looks like this. You can see immediately that it seems to make sense. More simple strings appear on top, so they are produced more frequently from computer programs, random computer programs. And values follow an exponential decay exactly as predicted by algorithmic probability, so it all conforms with the theory. We can see that most Turing machines produce a simple 0 or 1 and halt, and so on. And while you may think that this table is sorted by string length, it is not. Here on the right are some cases of longer strings that appear higher in the ranking because they are simpler. We call these strings jumpers because they are far away from their length size group. By looking at this table and jumpers, one can see algorithmic probability in action. One other advantage of precomputing this empirical distribution is that while its calculation is intractable in the best case, and it is the most intensive computation possible because it is bounded and even equivalent to calculating the Beaver function, which we know are the most demanding computer programs, we only need to calculate all these once. Because once calculated, one can implement a lookup table with keys with as keys the strings themselves, and the application of the method becomes linear because one has only to look for the string and its associated value and not to compute again all the possible computer programs to get that value. Only if we are interested in the computer program behind once that there's something interesting, then we go to the enumeration and we find the specific computer program that was producing that piece of data or the set of computer programs producing that data. Of course, in the general case, completing this distribution is uncomputable and thus it is unachievable. But this also means we will always have a work to do, keeping us busy to make improvements upon previous estimations. On the left table, we have the table without considering the machines that never halted. But on the right, we have also the machines that never halted, identified by an empty string epsilon. And indeed, it turns out that 80% of Turing machines don't halt in this rule space length. And the greater the rule space, the more computer programs that halt. Still, by increasing the number of computer programs, we produce more strings and we can cover more cases. But all these numbers and the distribution and the number of machines that halt versus they don't halt, they all conform with the theoretical expectation. There is something else that may be of concern. That is the enumeration or the Turing machine model chosen and its effect on the empirical distribution. As you may remember, by looking at the sketch on the bottom, reproduced from one of the previous units, the invariance theorem tells us that we cannot be sure how fast the values of algorithmic complexity will converge in the face of changes of reference universal Turing machine or Turing complete programming language, even though the same theorem also tells us that eventually all values will converge up to some constant. So this would be a concern to our approach. How can we know if we are far off from estimations and that taking this particular enumeration from shorter to larger computer programs, even if it looks very natural, is perhaps unstable at the beginning? Well, our numerical calculations suggest that this is not the case. We have shown that the method is well behaved in several ways and seems not to diverge because in exploring greater rule spaces according to increasing Turing machine size, the output distributions converge while the differences remain very small and thus under apparent control. Notice that no other method is immune to this problem, including lossless compression algorithms. That is, which lossless compression algorithm one has to choose in order to guarantee faster convergence, and one cannot never know. One can only see whether something is working correctly or conforms with the theory. which is in our case the case.